Hello everyone, welcome to another Watch Me Do Math video. Today's video is going to be about this physics question you see in front of you. It's from the 2014, maybe the 2015 to 2016 paper, I'm not sure, from the round 1 of the British Physics Olympiad. And the reason that I particularly liked this question and that I wanted to share it with you all is because of two factors. So the first factor is that the actual physical ideas behind this question are quite simple. And so it's a question that even though it's in an Olympiad paper, it's accessible to anyone with an understanding of a couple of simple concepts that I'm going to talk about in a moment when I go about solving it. And these are concepts from chemistry as well as from maths. And the second thing I wanted to talk about, the most difficult pure physics element of this question is power is energy over time. And perhaps a little more than that, obviously, but generally the physics in this question is not too hard. There's a bit of difficult chemistry, which could also be applied physics, be considered applied physics, to do with this question and converting from wavelengths to energy of photon, which I'm also going to talk about in the future. But the second reason that I wanted to show you guys this question is because I think it makes a very good point about using infinitesimal quantities to solve a problem. So what do I mean by infinitesimal quantities? Well, I mean like d this, d that, delta this, delta that. So like dx, dy, delta r, delta a, delta q, etc. All of these things are either actually equal to 0 or they are approximately 0, and you can use the ratios between them in the form of derivatives, like an expression like dy over dx, as a tool for problem solving, especially considering that you can do something like this. Despite both terms being technically equal to 0 or very close to 0, you can still do something like this to help you solve the problem. And I think it's a really excellent technique to think about if you're trying to get your head around the idea of infinitesimal quantities as it is first presented to you in calculus, so that notation like the notation for a derivative, dy over dx, and the notation for that of an integral, which although will not be covered in this video, has been covered many times on my channel before, like the big S and then dx, make more sense to you if you think of the quantities dx, if you think of the quantity dx as a infinitesimally small change in something, i.e. a change in x, or a change in y, or a change in the radius, a change in the area, a change in the charge, etc., etc. So, if I need to reset up my drawing toolbar here because it's been a while since I did a purely drawn video, but I am now on a larger computer which has more USB ports, and so I have a mouse at the same time, so I don't have to do some awkward things like dragging an entire page of working off the screen manually with a pen. But anyways, let's begin. So a monochromatic sodium lamp of wavelength lambda is equal to 6 times 10 to the minus 7 meters radiates 100 watts of radiation uniformly in all directions. At what distance from the lamp will the photons have an average density of 10 to the power of 6 photons per meter cubed? So how should we think about this question? Well, it seems to me like the question is using the quantized model of light as little photons rather than as a continuous wave, to think about the light that is being emitted from the lamp. So in this model, you would have some lamp, and from it, due to whatever is exciting the lamp, packets of light called photons are emitted. And as opposed to the wave model of light, these are discrete objects which fly through space at the speed of light and have a certain amount of energy contained within them, and no more and no less. Unlike a wave, they cannot be divided into infinitely many pieces. There is just, you have some integer number of these packets flying around. And so what it means by the average density is it's telling us that there is a certain distance away from the center, the point source of light, at which every meter cubed, if that exact point in space was replicated across a meter cubed of volume, would have 1 million photons in it. And the clue that tips me off to the fact that you need to use infinitesimal quantity to solve this problem is that it's asking for a distance from the lab. It is essentially saying that at any distance, at any single point in space, there can be a particular density of photons, even though it is only a point in space rather than any volume in space, which is what you'd expect when you look for a density, in the sense that your density, rho, might be equal to the number of photons divided by the volume of a space with photons within it. But again, as we know, all of the photons are at points with varying density, as in there are photons closer together when they've just been emitted from the light source, and there are photons more spread out when they have traveled a distance and been able to spread out. And at any point in space, even though it's ridiculously unlikely that that particular point will have a photon actually in it, you would still be able to calculate a photon density, because you take this infinitesimally small volume, calling it dV, or delta V. I'm going to draw it with a capital V for volume. And you would say, oh, in this space, there's going to be an infinitesimal number of photons, dn, or delta n, so dn or delta n, that represents the number of photons that would be in here. And while both of these quantities would technically be zero, the ratio between them at a particular point in space, at a particular distance away from the middle of the lamp, would be that photon density that we are looking for, dn over dv. It is like if you had a non-uniform mass, for instance, a human being. This is my approximation of a human being. And say you took like a random point in their body. Even though that particular point is unlikely to have any mass whatsoever within it, you could still say that that point has a certain density based on the gradient of densities around it. As in, if you had like a cube of iron and you knew it was all iron, then while you could still calculate average density from the idea that rho is m over v, you could calculate the density at a particular point, knowing that rho is equal to dm over dv, where dv was a tiny volume that represented the volume that that point contained, which would be equal to 0, and dm is the infinitesimally small amount of mass of iron that's within that point, and it would be equal to the actual density of the iron in general. It's just that it's measured over an infinitely small space. So that's what's interesting about this problem. So to go about solving it, we've come to the idea that we're looking for that ratio dn over dv, right? So if I just get rid of this for a moment, we want to find the radius r such that dn over dv is equal to 10 to the 6. So how might we go from here to here? Well, let's think about what quantities we know. First, let's think about the actual amount of photons emitted by the lamp every second. This would be the first most easy thing to think about, dn over dt, because it's something that we can use the typical sort of physics problem-solving mindset to approach. We know that the number of photons per second is going to be dependent on the power of the lamp, as well as the energy that is contained within each photon. And we can actually express this in the form of more infinitesimals, or more derivatives. For instance, if there is a certain amount of energy per photon, which is constant, then we could say that an infinitesimal amount of energy would correspond to a certain infinitesimal amount of photons, right? So let's remove this equal sign for a minute because we're just considering the problem-solving tools we could use. If there is, for instance, a certain amount of energy contained in every photon, then for an infinitesimally small number of photons, a corresponding infinitesimally small quantity of energy would be used to make that many photons, right? And we could further think about this infinitesimally small amount of energy to get this dt, in the sense that dE by dt is going to be the power released by the lamp. Because that's given in the question. That's a piece of data we know about the experimental situation already. 100 watts is the amount of power emanated by the lamp. 100 joules of energy per second, or some corresponding amount of energy over that particular amount of time. So the first thing I want to consider is that to get dN by dt, the number of photons emitted per second, from dE by dt, the energy emanated from the lamp per second, we're going to want the number of photons per unit energy, dN by dE. So how do we do this? Well, the equation that you usually consider when you are talking about photons in a physics sense, emanating from a whatever, having a certain amount of energy, is this equation, E is equal to hf, where E is the energy of a particular photon, h is a physical constant called Planck's constant, and which essentially tells us the relationship between the amount of energy in a photon and the frequency of that photon. And f is, as I just said, the frequency of the light coming out of that photon. So this does not actually help us directly because we don't know the frequency of the photon as it stands. However, we can use the wave equation, which is the idea that the speed of a wave is equal to the wavelength times the number of times the wavelength is traveled through every second, which is also considered the frequency. F, for instance, if I had a certain wavelength lambda and there was a wave that went through 3 lambdas every second, I'd know that there would be 3 lambdas of distance covered every single second, if this was the frequency, right? So my velocity would be 3 lambdas per second. Anyway, that's sort of the logic behind that particular formula. But let's keep thinking about this. C is equal to lambda f, where lambda is the wavelength of the light and f is the frequency of the light. So if C is equal to lambda f, then f is c over lambda, and our final formula for the amount of energy in a particular photon becomes E is equal to hc over F. And again, if you have n photons, then the total number of energy is going to be E is equal to the number of photons n times the number of energy in a single photon. And while one way of thinking about it is you could go directly from this equation to the expression dE by dN is hc over F, from the fact that this E already represents a unit of energy contained within each photon, perhaps describable in joules per photon, rather than being a pure joules-based quantity. We could also consider this to take a more mathematical route of differentiating both sides of this equation with respect to n when we talk about just a total amount of energy, a number of photons involved in units of photons, and that ratio that links them together. But anyway, we come back to the idea that, oh, this is not F, this is lambda. We come back to the idea that it's hc over lambda. So if you'll give me a moment, I'm going to get rid of all of this so we can continue working. If dN by dE, the number of photons per unit energy, is the opposite ratio to the energy per photon, which it is, mathematically speaking, because you could kind of treat these quantities representing real physical things as just actual quantities that can be manipulated in a fraction like this, then given that this is equal to hc over lambda, then dN by dE is lambda over hc. The next thing to think about is that dE by dt is just 100, because it's the amount of energy, the infinitesimally small unit of energy, dE, per unit time, dt, or power, being 100 watts. So what are we missing here? We have the number of photons emanated from the light every second, dN by dt, and that is 100 lambda over hc. But where do we go from here? Well, one thing I want you to consider is think back to what we're actually trying to find, dV by dt. No, not dV by dt, dN by dV. We have already worked out these quantities. dE by dN is hc over lambda, so dN by dE is lambda over hc. Multiplying this and this together, getting us dN by dt is 100 lambda over hc. Or in fact, we could just write this as the power times lambda over hc. And we want to remember that we're looking for the density of photons at a particular point in space, dN by dV. How to get from dN by dt to dN by dV? Well, to do that, the first thing that comes to mind is we need to multiply by dt again, and we need to divide by dV somehow. Now this quantity by itself dt by dv. It doesn't really mean anything to me, if I'm going to be honest. It seems like sort of meaningless mathematical consequence of other quantities, which it is. So let's think about the situation in a physical sense before returning to the world of mathematics, because this is naturally what you do when you're at a loss with the mathematics in a particular physics problem. We have some amount of photons that are emanated every second. So given that light moves at a particular speed, if you were to go away through 1 light second, if you were to go away to the sphere with a distance of 1 light second, or 1 cs, which is the speed of light times a second, if you were to go this distance away, then you'd see 100 lambda over hc photons in this entire sphere. And you'd be able to calculate an average density for this quite easily. But this is not everything it seems. What you want to consider is that you're really looking for an amount of photons dn that is contained within this sphere at the point that it just left the light. And the sphere is some speed away from the result of light traveling for a certain amount of time dt, so c dt. So dn of photons are everywhere in here, and this is c dt, the radius, basically, of the space that contains dn of photons. And as you move outwards, this initial blob of photons around the point source of light, if you take it to be a point source of light, which we've been instructed to in the question, becomes a shell of photons containing dn of photons, moving away from the center. So this shell is going to be of the same radius across. It's still going to be c times dt in distance across, and it's still going to contain dn of photons. And if we can calculate the volume of this space at a particular radius r away from the lamp, then we can call this space to have an infinitesimally small volume dv, and use that information to finally calculate dn by dv based on this dt by dv idea. So let's consider this for a moment. dn of photons is going to be, in this geometric shape, a sort of a shell of a sphere with total volume dv and thickness c dt, because this is the distance that the photons have traveled in the particular time dt. And this just comes from the fact that when the light is first released, it makes a sphere with this radius c dt. So how do we deal with this? Well, because the shape itself, the 3D shape which contains all these photons, is so thin, we can approximate it using the formula for a surface area of a sphere. If you have this infinitesimal volume you want to find, then it's going to be equal to whatever area the volume is made out of, since it's basically a 2D shape in a 3D universe. So some surface area of the sphere, A, multiplied by the radius or thickness of that sphere. And given that this thickness is c dt, And given the fact that we know that the area of a sphere away from the center is going to be 4 pi r squared, we come up with the idea that dv by dt is 4 pi r squared c. And again, this quantity doesn't actually tell us so much. And so there's something I want you to consider as well. C is, like, we found the answer, but I don't want to finish talking about it just yet, basically, because think about it this way. C is a measure of how fast this bubble of photons, this initial sphere of photons, spreads out into the universe over time. C is the speed of light. It is essentially how fast this radius of the shell increases, because we know that this shell is always going to have the same radius dr, the same thickness dr, which is equal to the speed of light times dt, this particular value. But I want you to consider that the speed of light, therefore, must be dr by dt. It's really difficult for me to explain fully the physical significance of this derivative, dr by dt. But essentially, I think you can think about it as if it were the speed at which the shell is expanding. And it's useful for only that, because it tells you that the thickness of this shell that you're working with is related to how fast the shell spreads out, and you can use that as a problem-solving tool to get this final quantity dv by dt, which is what you wanted to find in the first place. So, in a sense, we're really saying that dv by dt is 4 pi r squared dr by dt, or if you multiply both sides by dt, taking the time element completely out of it, dv is equal to 4 pi r squared dr. Now, where might you have seen this before? Because if you think about it, it's saying that the volume of a particular surface of a sphere, where that surface is r away from the center, is going to be 4 pi r squared multiplied by the thickness of that surface, dr. If you integrate both sides, you get the integral of dv is equal to the integral of 4 pi r squared dr with respect to r, or v is 4 over 3 pi r cubed. Isn't that amazing? It's the formula for the volume of a sphere, and it came out of this problem-solving question that you might not have expected it to. The reason that these 3D shapes behave like this is because the integral is just a way of continuously summing up an infinite number of an infinitely small quantity. In this sense, by adding up together the volumes of these layers, onion-like layers, of a sphere, where each layer has a certain surface area, will get you to this overall volume, because each dv, or each 4 pi r squared dr, represents a real physical thing, this infinitely thin layer of volume around a sphere. You can get to this final answer, v is 4 over 3 pi r cubed, and you can see why. Well, there should be a plus c somewhere, but I don't know how to deal with this off the top of my head. You can see why dv by dr, this surface area, would be 4 pi r squared. Hopefully you can see also how this makes sense when you're looking at other formulas of 3D shapes, other other, what do you call it, volume formulas for 3D shapes. So anyway, going back to the question at hand, we know that dV by dt is 4 pi r squared c. Again, I don't entirely know how to explain the significance of this in a fluent way, but if dN by dt is that, and dV by dt is 4 pi r squared c, then it should follow that you can find dt by dV by taking the reciprocal of this, or 1 over 4 pi r squared c. In a sense, dN by, what am I looking at again? dN by dV, the density of photons, is equal to p lambda, power times wavelength, over 4 pi r squared, and then a factor of 1 over Planck's constant, and then a factor of the speed of light squared. And that is the photon density a particular radius away. So having derived this formula, dN by dV is p lambda over 4 pi r squared hc squared, you can rearrange basically with the knowledge that, I'm going to tone down the size of my writing, dN by dV is meant to be 10 to the 6 photons per meter cubed. P is 100 watts. Lambda is 6.0 times 10 to the 7 meters to the minus 7 meters. R is an unknown. H is Planck's constant, which I'm just going to look it up here. Planck's constant. 6.63 times 10 to the minus 34. And c is the speed of light, or 3.0 times 10 to the 8 meters per second. And overall, putting all of this into a rearranged version of this formula that I've just explained to you where it comes from, we get dV by dN is 4 pi r squared hc squared over p lambda, or r is the square root of dV by dN times power lambda on top and hc squared and 4 pi on the bottom, to be put into a graphing calculator, where I'm just going to pause the recording for a moment. Oh, another note is that dV by dN is going to be 1 over 1 million rather than 1 million as suggested from the question. And after putting this into a graphical calculator, you get an ultimate result of R is equal to 283 meters. So that tells you that 283 meters away from a sodium lamp with those characteristics as described in the question, you will have a photon density of 1 million photons per cubic meter. So this is also equivalent to 1 photon per square centimeter. So it's actually really, really tiny if you think about it, this 10 to the 6 per meter cubed value, especially considering that 1 photon contains such a pitifully small amount of energy. So that's, I don't know, that's why I love this question so much, because it introduces you, it forces you to think about a lot of cool ideas about, for instance, the nature of 3D shape formulas coming out of adding up little slices of them together, as well as the idea that, for instance, 2D shape formulas are also formed in to some extent in this way. For instance, the circle is like if each piece of area is some onion ring, it's some onion ring times where this onion ring is 2 pi r, where pi is a value that is defined explicitly based on this relationship between r and the size of the 2D ring. If dA is 2 pi r dr, then you can see that a is pi r squared, right, from integration. That's an interesting thing to think about in the sense of 2D and 3D shapes and how their formulas all come out. And it really goes to show that this tool, this ability to think about infinitesimal quantities, is a very useful tool in problem solving in physics and maths. So if you enjoyed this video and you found it either helpful or you just found it interesting, then I encourage you to subscribe to the channel, and new videos are posted every Sunday on maths and physics topics I like or about examinations. And I'll see you next time. Until then, bye-bye.